Alright, we're ready to start our voyage into basically the last chapters of this semester, and so we're going to talk about waves. And so this embarks chapter 9 and chapter 11, so we're going to do most of chapter 9, but we're also going to add in a little bit of chapter 11. So here we go. So this is the introduction into waves. So what is a wave? A wave is just a repeating disturbance or movement that transfers energy through matter and space. So it's something that basically moves through matter. It's considered a disturbance. Maybe an example of a wave would be the energy that is transferred during an earthquake. So those waves travel through the earth. That's an example of a wave. Keep in mind that waves carry energy. So an example of this would be that a pebble falls into a pool of water and those ripples form. And because it's moving, the falling pebble has energy, remember? Because it has kinetic energy because it's moving, so it has that kinetic energy. And so once it splashes in the pool, remember, that kinetic energy has to go somewhere. So it transfers some of that energy to the water molecules. And so that energy is in the form of a wave. And so waves carry energy. Now, some waves travel through a medium. That's what we call it when they actually travel through something. So mediums can be solids, they can be liquids, they can be gases. Sometimes you get a combination of these. But anytime it travels through an actual something, we call that a medium. Now keep in mind though that not all waves need mediums to travel through. A great example of this are waves that travel through space, right? Space, outer space, is a vacuum, meaning that it has no matter whatsoever. So like for example, if we have a satellite out in space, that radio waves or satellite waves, they don't necessarily need, or they don't have any medium to travel through there because there's no particles to travel through. Light, UV rays, they don't need any medium to travel through because the sun is going straight down to Earth. So there's different types of waves that don't necessarily need anything to travel through. They do not need a medium to travel through. So keep that in mind, that not all waves necessarily need a medium. Some do, some do not. Okay, the first type of wave we're going to talk about is a mechanical wave. Okay, and so waves that can only travel through matter. So these are things that do need a medium. So you have to have a medium for this to actually function or travel through. So they have to have matter, they have to have a medium. So no medium, can't work. Now, they include two types of waves, transverse and longitudinal. So these are the two types of waves that make up mechanical waves. Okay, so we break mechanical waves into two categories, transverse, longitudinal, and they require a medium to travel. Okay. So, we'll specifically now talk about a transverse wave. A transverse wave is where the matter in the medium moves back and forth at right angles, is what it's considered, to the direction of the wave. Now, I think this is better just to look at it a visual, like this whole definition thing is kind of confusing. I mean, obviously we need to learn the definition because it's physics, you have to learn definitions, but look at the picture, kind of logical. This person with the rope goes up and down, up and down, up and down. It's hills and valleys. That's what a transverse wave is. Okay, so the rope is traveling horizontal as the ropes move vertically up and down. So it's kind of like your typical like jump rope. Somebody's gonna, jump up and down, that type of thing. That's a transverse wave. It's like if you watch kind of like music on a, if you're going to cut music or something, that's a transverse wave. Okay. Now the second type we have is a longitudinal wave. Now you could kind of think of this in the terms that it's long, so longitudinal. This is we say the definition is the matter in the medium moves back and forth with the same direction that the wave travels. Okay, the easiest way, again, look at the picture. It's a coil. It's like a spring toy. If you've ever seen a slinky, that's what it looks like. The wave goes out. Okay, that's basically the idea of the longitudinal wave. It's long, it goes outward in a circular path. So the wave goes out in a circular direction to where it's going. That's the idea of a longitudinal wave. Now, the idea too of a longitudinal wave is that you can squeeze several coils together at one end and let go of the coils. It looks like the whole spring is moving, but actually what's happening is that the coil itself carries the energy down. That's why we call these guys also compressional waves instead of, because not that the whole toy moves. It's not like a true like spring effect where you pull the spring back and it bounces out. It travels down the spring itself. If I kind of go back to the last picture, I know some of you are going to scream at me, but I'm going to go back here. So it's this picture. If I compress a couple of these coils, the energy is going to go down the coil versus springing out. I'll go back here so you guys can fill out your notes. I'll pause for a second. So just make sure that you understand that they're compressional waves, meaning that they're going to go down the length of the spring versus being a compressed, where it springs out. It's not truly a spring, it's a traveling thing. Sound waves are longitudinal waves. So when you like slam your locker door shut, for example, it vibrates, it compacts those sound waves near your locker, and then it pushes out. So it travels in a circular pattern. So it travels circular pattern out towards, everything else. So that's why, it goes through the air and it makes a wave and eventually gets to your ear and you hear that loud noise. Okay, because it compresses all that and all that's pushed together versus the longitudinal wave. Sound's kind of cool because it could travel through other mediums other than air, like water. Like a lot of people have heard that. You go into a pool or something and you can hear people talk. It could travel through wood. We know that. Instruments. I think of all the instruments that are made out of wood. And so when it reaches your ear, it causes your ear to vibrate, and it sends signals to your brain. And so sound is really cool. Like the study of sound is just interesting. I mean, how sound actually works. Why does this do this every time I record here? So there you go. Water waves. Water waves are pretty interesting because we look at water and we think, oh, water goes up and down, up and down, up and down, up and down, up and down. Well, water's not purely a transverse wave, though, even though, look at that pattern, it looks up and down, up and down. So it's not purely a transverse wave. Water also, down within the surface itself, it also has a circular pattern. So it not only moves up and down, it also moves back and forth as well. So that means that it is not only a transverse wave, it is also a longitudinal wave. So it has both types of basically contains both mechanical waves, the transverse and longitudinal waves. So make sure that you're aware of that it's not purely a transverse wave. So the water is pushed back and forth to form those crests and troughs. And we'll get into some of this crest and trough thing here in the next section about defining the terms of a wave. So waves, of course, are occurred by the fact that the wind blows across the ocean. The size of the waves depends on the wind speed, the distance over which the wind blows, and how long the wind blows for. So you could tell basically how well waves are going to be or how high winds are going to be basically by studying wind speed. You can study how long the wind's been blowing for, and of course surfers study a lot of this stuff just to determine, they watch the weather, they watch different things in order to determine how well the surf's going to be that day. Okay, seismic waves. We don't have to deal with a lot with this in Indiana, but of course sometimes once in a while we have to deal with a seismic wave. Basically, we have these things called tectonic plates. And that's basically where the earth comes together, these plates within the earth themselves. And so what happens is that suddenly they decide to slide past one another. They actually are moving always, but they move with such small distances all the time that it usually doesn't matter. But sometimes they move a lot more than what they need to, and that's what causes these seismic waves. And that produces energy. And when these tectonic plates produces this energy, and we call these fault lines where these plates are. This energy produces seismic waves, or these seismic waves produce energy, and so we call that an earthquake. Seismic waves are a combination of longitudinal and transverse waves. They could travel through the earth and along the earth's surface. So they're not only longitudinal, but they're also transverse, just like water waves. And so they go across the earth's surface. The more the crust moves, the more energy is released. So wherever those tectonic plates are, the more that they slip, the more they move, that's the worse the earthquake is. So, we hope, that's why Indiana doesn't get bad earthquakes, because we're not on those big fault lines, and so we don't have to worry about that as much as some places that have larger fault lines. We're going to look at a little video here just showing you a little bit more about earthquakes, just to show you about so you can see the transverse and the longitudinal waves a little bit better, and then we'll be done with the notes.
Rocks break and move along surfaces called faults. When movement occurs along a fault, an earthquake results. The earthquake releases energy from a point in Earth's interior called the focus. Seismic waves travel outward from the epicenter and are received at a seismograph. The first seismic wave to reach the seismograph is the primary or compressional wave. They are the fastest of seismic waves. The second wave to reach the seismograph is the secondary wave. Secondary waves travel through Earth more slowly than primary waves. The movement experienced during an earthquake is caused by seismic waves traveling outward from the focus. Primary waves move through Earth by causing rock particles to move back and forth in the same direction as the waves are traveling. Secondary waves travel through Earth by causing rock particles to move at right angles to the direction of the waves. The slowest type of seismic waves travel along the surface, giving rock particles both an elliptical motion and a back-and-forth swaying motion. These surface waves cause the most damage to buildings and other structures during earthquakes.